Good afternoon, everyone. Murala sir, can you hear me?
Yes, yes, I can hear.
Yes, sir. Please check if you are able to share your
Am,
screen.
am I audible?
Yes, sir, you are also audible.
Okay. Uh, Jasdeep, I will call you later. Hello?
Yes, sir.
Yeah. My screen,
Yes.
is it visible?
Yes, sir, your screen is visible.
Okay.
We will start at 12:15.
Okay, no problem.
Yeah. Thank you, sir. Good afternoon, everyone. Myself, Anushri from Indira Gandhi Delhi Technical University for Women, welcomes you all for the next session. For this session, we have Dr. Subramaniam Murala from IIT Ropar with us. Dr. Murala has PhD and MTech degrees from the Department of Electrical Engineering, IIT Roorkee. He has received his BE degree in Electrical and Electronics Engineering from Andhra University, Andhra Pradesh. He was a postdoctoral researcher in the Department of Electrical and Computer Engineering at University of Windsor, Canada. Mr. Murala has published multiple research papers in esteemed international journals and conferences. His major research fields of interest are image retrieval, computer vision, medical image processing, and object detection. In this session, he will be enhancing our knowledge on the topic generative models for video surveillance applications. So I request Dr. Murala to address our attendees.
Yeah. Good afternoon and thank you very much for the introduction. And uh, in today's lecture, I'm going to discuss about the deep generative models for video surveillance applications. And she already explained about myself, like myself, Subramaniam Murala. I am from IIT Ropar, Rupnagar, Punjab. And now coming to the actual topic, like deep generative models for video surveillance applications. For this, actually, we need to discuss about the generative models like generative adversarial networks or autoencoders. So, before starting of this particular topic, I would like to know that whether this topic was covered by other experts or I should cover it. I'm just asking, means, what's your name, ma'am?
No, sir, not covered by anyone. You
Not
can
cover.
continue.
Okay, okay. Just a minute. I'm just sharing that. Okay, so then let me explain about the deep generative models for computer vision. So here I may take around 45 minutes to discuss about this topic. Then I will go for the application, especially for the video surveillance applications. It is a motion detection or moving object detection. So that I will be discussing here after the generative adversarial networks, and before that I will be discussing about the autoencoders. So here generative models means like using deep learning, we are going to develop an algorithm or deep learning networks which generates the content, which is totally different from the classification. So before of generative adversarial networks, autoencoders were proposed, and in autoencoders are also task of autoencoders also similar to the generation, only data generation. So first let me explain what are the major differences between these five topics, so that I think you can clearly understand what exactly what. So first one is supervised learning. So I think you are already aware of this, what is called supervised learning. If you train your algorithm, or if you any deep learning or machine learning algorithm using specific labels, means if for a given training input data, if you are having a labels or ground truths, and if you train that particular algorithm with labels as well as input, or input along with the labels, then we call that is a supervised learning. So if it is different, like without labels, you need to train the network, and you need to reach the specific target. If that is the case, it is unsupervised learning. If I give an example, face recognition algorithm, it's a classification problem. If I go for a face recognition, means training data having input faces and corresponding label, it belongs to person A, person B, and so on, person Z. So these are all the different types of different classes, and we need to classify them, and that information ground truth is also available with us. So while training, we will cross verify whether this is training appropriately by considering the ground truth labels and predicted labels. We will compare, and based on that we will go for the back propagation if it is ML based algorithms. So based on that we will update the weights of the neural network, and then we will go for the next iteration. So this is generally the process for supervised learning. In unsupervised learning, if it is learning based algorithms, so there are no ground truths, but we need to reach the target. So just best example, it is not exactly learning, but it is kind of optimization algorithm, that is like clustering algorithms. If you look at the k-mean or fuzzy c-mean algorithm, these are all kind of optimization algorithms to reach the target, but there are no specific labels. Ground truths are not there while training of these particular algorithms. Here what you can do, like let's say given input image is there, and you need to segment them appropriately based on the either semantic information, or based on the color, or based on the structure. It depends upon your target. So based on that you have to develop the algorithm. So if it is based on the k-mean algorithm, is especially works for the kind of if it is for 3 channel means RGB channels, mostly it works for the color information of clustering. So based on the color content which present in the image. So there we doesn't have any kind of ground truth. Our target is only how many clusters you need to make. So I am giving input image, and I need to make 5 clusters or 6 clusters or n clusters. So there we are just specifying there means, and we are not providing any kind of ground truth. So that particular procedure we call it as unsupervised learning. And these two means next one is semi-supervised learning. Semi-supervised means like if you are having n samples of data for training purpose, but you doesn't have the labels for all n samples. You are having few samples, and remaining few samples you need to predict, or you need to learn still without having the ground truth. So it is neither fully supervised nor fully unsupervised. That is the reason we call it as semi-supervised. So best example is like if I'm having a video of 1000 frames, but first 5 to 10 frames ground truth or labels are with me. So by utilizing the first 5 to 10 ground truths, labels ground truths, I need to predict the content for remaining labels, remaining frames. So this is a kind of procedure for semi-supervised learning. So these three, whatever I am discussing, supervised, semi-supervised, and unsupervised, these all three can be applicable for either classification or regression problem. So let me explain what is called classification problem. Classification is kind of categorization of the content or categorization of the samples. So in face recognition case, we need to recognize that particular faces belongs to whom. So that is a kind of face of A, face of B, face of C. Like that, these are all the classes like A to Z. These are all 26 classes are there, and we need to classify the input data. It may belongs to any one of these 26. So that is the kind of categorization. I need to label. I need to predict the class of that particular input sample. But next one is a kind of next fifth one is a regression problem. Regression means it is not a prediction of the label or not prediction of the category. It is a prediction of some information. So it is a floating point numbers. It is exactly like a best example for this regression problem is weather forecasting. If I want to know the if I want to predict the temperature tomorrow temperature at Roper on tomorrow at 10 a.m. What should be the temperature if I want to get it? So that time I need to have the data of previous 1 year data. If it is with me, I need to predict what will be the temperature for tomorrow at 10 p.m. 10 a.m. So at that time, it is a kind of temperature cannot be a kind of class. It is a kind of floating point number. It may be 30 degrees, 35 degrees, or 35.1 degree, and so on. It can be anything. It is a kind of floating point number, and there is a range maybe between 20 to 35 or 40. So within this range, it will come, but these are all floating point number. This is a kind of problem of regression problem. So even like data restoration or image restoration or image denoising, these are all comes under the category of regression problems, and remaining like uh, recognition parts, all these are belongs to the classification problem. So these semi-supervised or semi-supervised or unsupervised, these are all these three is a learning procedure, and it can be for either classification problem or it may be for regression problem. So if you understand this one, main target here is like auto encoders, especially we are targeting only for regression problems. Regression means we are not targeting for the classification purpose. Autoencoders are especially developed for the regression problem. It can be like denoising or image restoration, or maybe for data generation. Input, I am giving certain data and I need to generate the pixels. Like that I need to do. So here autoencoders case, like in name itself, it is saying that automatically it encodes the data, and then the data will be utilized or transformed to the different form to generate the other form of information. So means some different information as per your target we need to generate, which means decoding. So you need to decode the data as per your requirement. Encoding is required accordingly also. So that is the reason, simply as it is an automatic algorithm, it involves two modules. One is encoding module and another one is a decoding module. For encoding module, whatever the data you are providing, that will be encoded or it will be performed or transformed into some other format where it is appropriate for the getting of more information for a given input data. So decoding is like appropriately in what manner you want to convert that particular data in data. So that is a kind of decoding module. So this totally I can we can see in the other perspective, like principal component analysis perspective, that I will explain how it is related to principal component analysis. So here encoding module means if I explain target case, let's say this is an input image here. So X, just a minute. So here if I am giving an input and I want to get the output. So let's say now if I want to target, input should be regenerated at the output. Means my target is that X dash should be equal to X. That is the target. So why I am doing like this means So especially I am doing some kind of transformations in between. So I am transforming capital X to Z, and again Z will be transformed back to the capital X, which is means X dash, which is my target is that I need to get back to the X only. So that is if I develop algorithm in such a manner. So this is like of kind of encoder and decoder, you can say compression problem. It's like compression means like encoder will try to decrease the computational complexity to store the data, to transmit the data. If I want to transmit the data from here to some other place, so that time if I am using a 4K resolution image, and 4K resolution means it is 16 megapixels, 4K by 4K image resolution. If I want to transmit here, 16 megapixels are there, and if I want to transmit that from here to there, it is very expensive. So in that to avoid this expensiveness, to decrease the complexity, so we can develop a kind of encoder which encodes the data into lower dimension, and at the decoder side I will decode appropriately. So here, while training of my autoencoder algorithm, I am just targeting that X should be regenerated at the output. So input should be regenerated at the output. Once this training is done, I will just simply divide this into two pieces. So this particular module, encoder module, will be at the generator, means like sender side, sending side, and decoder module will be at the receiver side. So when sender is just converting the data or encoding the data and transmitting with less memory, means like less number of bits. Like if 4K by 4K, or if I'm taking 100 by 100 image, I'm having 10,000 pixels to transmit. If it is grayscale image, if it is color image, it will be again into 3. So 30,000 pixels are required to transmit from here to there. So, but if I apply a kind of encoder and downsampling to 10 by 10, I just need to transmit only 100 pixels only. So, but at the time of decoder, I know in what manner I have encoded. In the same manner, I will try to decode. So, in the same manner, if I decode, I am able to reach the accuracy of 99% of input. If I am approaching the output, which is 99% of similar to the input, so it is almost solving the purpose. So with very less complexity, we are able to process the transmission, and 99% we are reaching, or even above 90%. That is also reasonable. So this is one of the best example for autoencoders. So similarly, you can convert the same algorithm in terms of denoising problem. That also we will discuss. But let me explain how this is can be converted into the mathematical representation. So let's say this encoder is a kind of transformation. So it's a kind of function it is performing. So X is the input, and I am transforming that to the H here, which means in the last figure it was Z. It is a Z here. So again, that one I am giving to the decoder input, and that is a function of G, and I will be getting R here. So whatever the output of R I am getting, so that output R will be regenerated version of the input. If I am doing this, it is a kind of principal component analysis. Principal PCA is working like in such a manner like dimension reductionality problem. If I am having a data of n dimensionality, so using eigenvalues and eigenvector corresponding eigenvectors, so I will pick the eigenvectors which are corresponding to the largest eigenvalues, few number of eigenvalues, and then I will be reconstructing my data. So that if I am able to reconstruct the data of above 90%, so that I will just transmit only these top 5% of eigenvectors, and then I will regenerate or regenerate my work, my data at the receiver side. So this is a kind of process for principal component analysis. But if I generalize this particular algorithm, autoencoders are a kind of non-linear principal component analysis, because PCA is a linear transformation process, but here autoencoders are non-linear transformation algorithm, because I am using neural network. When I am using neural network with more than one with more than means even one or more, if I'm using hidden layers in between the input and output layer, definitely even one or more, it will be definitely non-linear transformation of my data. So that's why, that's why we can call it as the non-linear principal component analysis or data transformation or dimension and directionality problem. This way we can see the this autoencoders, and this whatever the content I am explained here, this is the kind of content I am giving here, and this is a kind of objective function. Whatever the output is coming from the decoder, I am targeting as input itself. I need to regenerate back. So that is this is a kind of objective function I need to use, or loss function, to minimize the loss so that I am able to regenerate the data. So here again, I can say that this is unsupervised learning process. My input itself is a ground truth. So that time it doesn't require any specific ground truth. Then we can simply call it as a unsupervised process. If I am going for compression algorithm, it is unsupervised process. So it is an unsupervised procedure. And coming to the application like denoising applications, autoencoder means denoising using autoencoders. So let's say this is my input image and noise image, and I need to regenerate the denoised image. So here, if I train this algorithm in a supervised manner, it will be good. So what I can do, input image, clean image I will collect, and on that I will apply some noise, and it may be kind of additive noise or maybe speckle noise, multiplicative noise, whatever it may be the case. And with that, I will train my network, and target is that denoised output should be generated. So Miss clean image will be considered as the ground truth, and noise added on clean image will be considered as the input. So this way we can run this particular process. It is a supervised learning process, and we can able to get the output using deep learning. So this particular process we call it as again data regeneration or data generation. So that's why we call it as autoencoders. And then again, these autoencoders have been used, proposed for the semantic segmentation or brain tumor segmentation. So they have utilized the kind of concept for unit architecture. So did you discuss the means other experts have discussed about convolution neural network or not? CNN?
Yes, sir. Was
Okay.
discussed.
So here we are using convolution layers, our pooling layer, convolution pooling, rectified linear unit, which is a nonlinear activation function. And similarly, we can means we use batch normalizations. With the combination of these layers, we can develop a CNN network. Here, CNN network is developed in the U-shaped structure. It is also very popular and well-known architecture for image segmentation, especially problem, and people are also using for the regression problems also. Means even the segmentation is also kind of regression. Segmentation is a pixel level classification problem. I need to classify each pixel belongs to either foreground or background or class of that. So that way I can say, so it is a kind of pixel level classification problem. It is neither fully classification problem nor fully regression problem, but we can say it is in between. So it is a kind of regeneration problem or classification of the labels of a pixel level. So that's why we can say we can apply this using autoencoders. So here I am giving input image. On that I am applying some convolutions of 64 channels. Further another again 64 channel again convolution, and pooling I am applying. And on that again I am processing. Further I am going for downsampling, and further I am going for the upsampling. So this way I am going for this particular portion is the encoder portion, and this remaining portion is the decoder, and this left side one is the encoder and right side one is the decoder one. So with this I am able to regenerate, means input image, input is an image and output is a segmented output. So this way it has been proposed for the segmentation problem. So the similar kind of problems I will be explaining in the video surveillance applications, which is a motion segmentation, which is exactly moving object segmentation. So now problems associated with the autoencoders enable to develop the generative adversarial network, which is called GANs. So in autoencoder's case, as we are having, it is simple CNN network. There is no much difference between uh, autoencoders or convolution neural networks. Both are same only. Now, just but interpretation only. And so here problem is like in backpropagation time. So I will be using labels and corresponding loss I am getting, and it will be backpropagated. But here one simple example I will give. Let's say as a instructor or as a supervisor, if I give some task to my student, and if I ask you to do this task by 15 days, so two ways I can do. I will just simply ask him the output after 15 days. That is one way. Other way, I will ask him the output for every 2 days or every one day, every day evening. I will ask him what is the output, whether you are reaching the target of 15 days or not. If I am doing these two ways, which one is appropriate? So obviously second one is the appropriate, because if I am cross verifying his output or his way of solving the problems, if I am able to see that, so if I'm tuning or if I am correcting it timely, so then it will definitely, he will be reaching the target within definitely 15 days. But if I see only after 15 days, so what happens if that way he has chosen, if it may be wrong, so that time it will be the total 15 days of hard work will be useless. So that this way also we can say, this is one example. So it means there is a kind of proper monitoring, timely monitoring or supervision. If I add on to the network, convolution neural network, so then definitely it will be a kind of better or improving the training process. So this is only the difference between the generative adversarial networks and autoencoders. We are going to keep one supervisor. So that supervisor is always checking what is the output, what output is coming from the generator. So from there it will be correct. Means if anything deviating from the target, automatically along with the actual loss, adversarial loss or supervisor loss will be given to the backpropagation algorithm, and through that we can definitely now through that we can definitely improve the training process. Okay, so this is only the case if I explain the content in module manner. So here generative models, again it is a learning for generation purpose, and adversarial means like a supervisor. So there is a supervisor, always supervisor says that no, you are doing this is wrong, that is wrong, or you are doing correct, go ahead. Like that is always a kind of opposition kind of thing is happening. So don't think like supervisor is a kind of opponent. It is a kind of path corrector. He will correct the path, whatever the student is moving, whether it is appropriate or not. So there is a kind of adversarial process, trying to oppose the wrong things and correcting the generator process. So it is a deep learning network. That's why we call it as a network. This is the called generative adversarial networks. If I talk about the means, let's say if I am giving so two images, and if I'm asking you a question, one image is generated by the computer using generative adversarial network, other one is the actual image. So can you say that which one is generated by computer and which one is actual? Based on your observation, can you say left side or right side generated by the computer?
Right side.
Right side is generated by computer?
Yes, sir.
No. Thing is that right side one is the target actually. See, once you observe in global level, it looks both looks same only. But when you see this particular portion, it is not able to regenerate the data very accurately. Means exactly exactly same as the target. It is not able to generate. Similarly, here also the case. So means we are able to reach the target, means not exactly same, we are closely reaching to the target. From this we can say any computerized algorithm generally performs the either equal to the ground truth or maybe less than to the ground truth. Generally it cannot give beyond the ground truth. It means your labels or ground truths are not correct. If it is giving your algorithm is better than the ground truth, which means your ground truth label is wrong. So this way. So now coming to the, if I interpret this means more applications, like I can regenerate the data with simple skeletons. Means if I'm just simply sketch this kind of sketch, if I give, I am able to generate this kind of data. And if I give any kind of mountain shape, I can able to generate the mountains. And if I'm giving the, here I did not give any sky region color, that's why different colors of sky regions are here. But if I give a specific color for the sky region, it will be giving the same color. So with this, you may think that this is a kind of magic only, but you may think like how it is generating. So it is not happening from heaven. Again, here there are specific way of training process is there, and it is very much applicable for specific specific applications. You can able to achieve the accuracy up to the level of commercial targets, commercial applications. You can reach, but here you need to work for a specific application. So because my training data is there appropriately, like my input is like of shapes, I will give triangle. If I give triangle, it will understand that, it will understand like I need to generate the mountain. If I give any kind of greenery, it means it should generate the greenery content. And then if I give kind of sky color, what color I want to give, appropriately same color it should generate. In the same fashion, I'm training my network. If I show the network how it is actually happening, so here in this, now if I give actual interpretation of this network or generative adversarial network, it is having again two modules. One is a generator module, and which is a generating process. Another one is a discriminator module, which is a supervisor here. So as I said, now we are adding on top of the autoencoder, supervisor is adding. So that is a discriminator. We are naming it as discriminator. Discriminator is nothing but trying to discriminate the content, whether it is appropriate or not, trying to identify that. Generator is simply autoencoders. So here now, autoencoders are nothing but convolution neural networks. Again, autoencoders are nothing but a generator in the GANs. So it is simply, generator itself is also a convolution neural network architecture, but target is as per the specific requirement. And then on top of that, I am adding a supervisor, that is a discriminator, and based on that, I will be checking whether generator is performing good or bad. So let's say here I am giving input image for any denoising algorithm, and target is here. This is the real world data. These are the target here. So that time, so these two inputs I am giving to the discriminator. So discriminator should able to identify X is a target, actually means a clean image, and this is the generated denoised image from the generator. If both look same, means it means my generator is able to generate the output which is exactly same as the ground truth of X. So it means discriminator will feel that as both are same. It means discriminator should be means will be fooled in such a manner. G of Z is again same as the ground truth. Means we are trying to fool the discriminator. Yes, I am generating the content which is exactly same as the ground truth. That time discriminator will be fooled. Discriminator will be diverted in such a manner. Yes, G of Z is as input. Means G of Z is a target data only. So with that, now we are able to achieve the target of X. So like that, in that fashion, it is if discriminator is simply identifying some mistakes of generator. So that will be feeded back to the convolution neural network, that back propagation, and accordingly it will be corrected and those weight parameters, and with that it will go for the next iteration. So that way this network will be trained. So main advantage of this algorithm is a supervisor discriminator is added on top of the autoencoder. Nothing else addition or nothing different from the autoencoder. This much only the difference. And again, one more thing, this discriminator is present only at the time of training. Once training is over, discriminator will be discarded because supervisor task is over. Once a student has been trained and he is now ready for the field work, like so, he has enough publications and he know how to guide the students. He got enough publications and he got the PhD degree. Now he is ready for the field work. He will get the grad means a degree from that place, and he will join in some other place. So generator is a kind of PhD student and the discriminator is a kind of supervisor. Once training is over, so both will be disjointed, and the generator target is that, again, target is to regenerate the data, to work out the data, to regenerate the data. And again, after some time, that is a different process. Generator will also work as a discriminator. That is different process. That don't link these two things. So here generator target is to get the output by supervision of the discriminator. So once training is over, at the testing phase, only generator will be present. Am I clear? If you are having any doubts, you can ask me in between only. It is not necessary to wait till end of my lectures. Okay, and now training process case, generally how to do? Generally we do, initially we will log the generator, because we need to strengthen the supervisor. Let's say student recently joined and he come up with a new topic of research, and even it may not be related to, or maybe exactly not related to his supervisor's topic. Maybe like I am working on computer vision, but there are so many topics are there in the computer vision also. If he comes with a different topic which is not in line to my current research topic, that time I should say that give me some time. So maybe 15 days time, I need to understand, I need to read about the content, and I need to strengthen myself. Then I can go for the supervision. So this is a kind of process again here. And first initially we will log the hyperparameters or backpropagation algorithm for the generator, and discriminator will be trained or backpropagated to strengthen the discriminator level. And once supervisor get trained with enough knowledge, then we will log the hyperparameters of the discriminator, and it will be back propagated. Means data, this whatever the gained content will be transferred or back propagated to the generator, and generator will be improved. Once this process is done, means after few epochs, both will be trained together, because supervisor is also having enough knowledge, and student is also gaining the knowledge with the help of supervisor. So after some time, both can work together. So student can bring some content and supervisor can see it, and automatically again he can guide. Supervisor can tell whether it is going appropriately or not. So that way it will go. So the same kind, this natural process only is happening here. And after few number of epochs, both will be trained in adversarial manner. So it means supervisor or discriminator is always correcting the generator of, means which is nothing but student here. This way it will be trained. Now coming to the objective function. So here supervisor target is trying to highlight the mistakes of the student, and student is trying to avoid those mistakes. If student takes it as a positively, so then definitely he will be improved. If he takes always I don't know why supervisor is targeting me only, he is saying that this is wrong, that is wrong, but he is not asking anything to my friend, so he don't like me. If student will feel in that fashion, and negative minded developed at the student also, so he will also, some attitude will be developed and it will be disturbed. So that is the reason, if ideal cases I am telling, if supervisor is genuine, definitely student should be genuine, and both will go very appropriately, both networks will work appropriately, and output results will be very appropriate. And now coming to the objective function. So as I said, discriminator is a kind of mistakes identification. That's why we call it as the maximization problem. Here loss maximization. Always discriminator is trying to identify the mistakes. It means loss of the generator is trying to predict, trying to identify them. So then discriminator is a kind of loss maximization problem, and generator is a kind of loss minimization problem. Whatever the mistakes are identified by the discriminator, that will be corrected uh, by generator. So now if I talk about the G of Z is the output of the generator, Z is an input image, and G of Z is an output of generator, and D of G of Z is the output of the discriminator, where G of Z, generator output, as the input. X is the real image label, real world image, and then d of x is the output of discriminator when I give real world images or ground truths as the input to the discriminator. So now this is the one, but now maybe you may get the doubt. So how this objective function has been developed? How like log d of x and log 1 minus d of g of z. Why not other side? So you may get this doubt. So if I explain this physical interpretation, so let's say x is a real world image, and if I am assuming it is a real image, means if discriminator is working perfectly, so it should identify that it is a real world image. And if I consider it is a kind of label 1, and if I am giving g of z, which is nothing but it is a fake image, it is not real world image, which is fake image generated by the generator. So it is definitely opposite label. Even you can take opposite also, but for opposite also I will be giving objective function. But without that, with this assumption, what objective function is coming, let me explain here. Let's say here x is 1. If I am giving x to the, it should be 1. And if I am giving g of z as input to the discriminator, d of g of z will be 0. This is the point. Means so if I check this, if I assume here again discriminator is very strong, it is very strong and enough to identify what input is coming, from where it is coming. Input either from real world generated by generator. So if it can able, means it is very strong. If I assume this way, what will be the output here? D of x. What will be the output of d of x? 1 or 0? 1 or 0? Yes, 1.
It's 1.
Yeah, you're right. It's 1. So that time log 1 means I'm just applying log transformation. Why I will tell later. So log 1 equal to 0. It means this particular content becomes 0. So here d of g of z will be, this will be again, this will be 0. It's like discriminant. I said discriminant is very strong. It means this will be 0, which means 1 minus 0, again log 1 is coming, this overall value is also 0. It means I am saying discriminator, this particular value is coming 0 and then this is a kind of loss value, and this loss value will be back propagated to the discriminator weight subdation. So as it is 0, so not necessary to train. It means back propagation is not required, which it means discriminator is strong, means strong enough to discriminate the inputs which are coming from either generator or maybe from the real world images. So if you think oppositely, so that time d of x, they actually should be 1 if it is strong, but if I said discriminator is not very good, it's not that much good. So if it is not no good, then it will be coming 0 only. Log 0 is the undefined function. Generally we will apply some epsilon term here. So we will apply some epsilon plus d of z in the training process or coding time we will add. So that time generally epsilon value we are keeping 10 power minus 12 or 10 power minus 8, like that we generally keep. So that time so here this one will be d of x is 0 and plus epsilon. So that will be kind of value, some value is coming log of that, and that will be propagated, which means this value that this requires of this discriminator is not strengthened enough to identify the inputs which are coming from either real world images or from the generator, like that. Even same thing is applicable right side also. There also second one also coming log epsilon plus 0 only. So that is a problem. So but this is for the way how we have developed the objective function or loss function for the discriminator. Similarly for the generator case, generator objective function is this one, log 1 minus d of z, d of g of z. This is an objective function. So here again this is a gradient calculation. for the stochastic gradient algorithm for the discriminator, and this is for the generator. Means gradient means first order derivative will be back propagated. But there is an issue, vanishing gradient problem in generator network. So that is called here vanishing gradient. Means at certain places strike the means like gradient will strike the again. So like if I take this one is a back propagation algorithm for loss calculation. So as I consider this one for the generator purpose, let's say if I am applying if discriminator is very strong, if discriminator is very strong, so it is simply saying that 0. So it is saying that 0 and log 1 it is 0. Log 0 is back propagated to the generator. I said this is a generator back propagation content. Then it will be coming, means going 0 for the back propagation of the generator. So when discriminator is very strong, generator is not training. So that is the reason we just apply derivative of this. So derivative of this, once I apply log x, which is nothing but 1 by x into derivative of this with respect to parameter, and then again this is a sigmoid function, because at the end of the network if I am keeping sigmoid layer, so that is a sigmoid function. If I apply derivative of sigmoid function, it will be sigma dash, it is nothing but sigma into 1 minus sigma. If you want the derivation, you just go through that. Sigma derivation of sigmoid function is sigmoid function into 1 minus sigmoid function. So that is an output. So in that case, these and this both are going off, and we are getting only this one. And now applying log function at this point. So this is the back propagation algorithm, back propagation content for the generator, and my back propagation content for the discriminator is the same only. Previous one, whatever I have explained. So now advantages of the generator. Generative adversarial networks, it is a generative process, generative procedure, and wherever you are using here, discriminator is added on this, and discriminator will be supervising the generator to approach the targets. So, and then it doesn't involve any kind of optimize maximum likelihood estimation, this kind of thing. It is simply training either in terms of supervised learning, or it may be an unsupervised learning process. So if real world images are not there, you have to train appropriately. If you see that there is a cyclic GAN, that is unsupervised learning process. So in an unsupervised learning process, unpaid learning process, there we doesn't have the ground truth labels, but we are having some labels, but these are not exactly ground truth labels. Accordingly, it will be performing. And so there means when compared to autoencoder, it is relatively better performance wise, because it is because of means extra supervision is added on that. That's why it is working better. And overfitting is generally less, but I'm not saying that there is no overfitting. Definitely there will be a overfitting problem, or model collapse may be there, or convergence also sometimes it's a problem. It may diverge, data may be diverged. So these are all the some real results, like where it is having issues. Left side one is the actual target, but right side is having model collapse results. So this is an problem. So to address these problems, like people have suggested, like batch size should be as low as possible, and generally we use batch size equal to 1. And then also some people suggested that you train your network with more than 2 labels, like classification I said real or fake. So real means it needs to make either 1 or 0, but if we do using different labels, fake is fake, and remaining real becomes again classified into different categories. But many people are not using this. It was just suggested, but in ground reality case, even this also we are not using real or fake. We are using just simply loss calculation from there. We are just getting the loss calculation from the output of the discriminator. Output of discriminator is also kind of feature vector, and that feature vector will be utilized for the loss calculation, and it will be back propagated for the generator as well as the discriminator appropriately. So this is the one. And now coming to alternative views of the labeling our objective functions. As I said, d of x equal to 1 and d of g of z equal to 0. So then this is a kind of objective function, loss functions. If you consider oppositely, so just interchanging of the content. Yeah, it is once you see this is the interchanging of the content is happening, and accordingly it will be your objective function or loss functions are getting changed. Now coming to the applications, there are so many applications here: image to image translation and text to image synthesis. Means with text I will be getting the image output I can synthesize, and face aging, I will be explaining like this, semantic segmentation. Either I can get the both side. If I'm giving left side image as input, this segmentation mask, I can generate this other opposite other direction. Similarly, this is all the case Google Maps case. It is like with structures or with simple map, and other one is day to night or night to daytime, or maybe summer to winter or winter to summer. I can generate the data. And similarly, simple labels, if structures are there, I can make the building structure. And very problematic and impossible problem in the image processing is like black and white image to, or which is nothing but grayscale image to color image generation. Appropriate generation of color image for a given grayscale image is actually not possible, but we can predict using deep learning, so using generative adversarial network. Other one is for industrial applications like leather industry. So to develop any bags industry, so some designer will be there, and he will always has to work with CAD software, and he has to develop the sketches. Then it will be decided which one is appropriate, and then it will go for the production. But here, if we use generative adversarial network, we can develop n number of combinations, n number of ways of designs, and immediately it can be done in faster manner, and it can be picked appropriate. The input is a kind of sketch we can generate, and GAN will generate the output very creatively, and that will be utilized for the production purpose based on the requirement. So these are all the kind of application. And face aging, like very popular app is face app. So how one can looks after 60 plus. So this is happening by considering the face of training with various combinations like input case generative adversarial network only. Face region will be detected, and that region will be changed skin color and skin tone, or some like structure of the skin as well as hair, and these things will be changed appropriately, and it will be regenerating the data. It is totally using generative adversarial networks to develop this data. Here the people are using, researchers are using autoencoders, which are nothing but generative adversarial networks only. So this is the kind of applications wise. And again, surveillance applications like moving object segmentation, that I will be discussing right now. After this generative adversarial networks, for this I think I will give 5 minutes break, 5 to 10 minutes break, and then we will start the actual applications for moving object segmentation. Is it okay?
Yes, sir. We have one query for this
Please, please.
presentation.
Yes, please. We can take
Is
up the queries.
GAN is GAN algorithm works well for transforming low to high resolution images?
Exactly, super resolution. But one thing is there, observation is there. You can use it, but there is an observation. We are also working on image super resolution in our laboratory. So, and we came across one point that if you are using generative adversarial networks, it is not outperforming the CNN models. Reason is that input data and output data, resolution wise, very closely when you see the content, then only you can see the actual difference. And generative adversarial networks is majority of content more concentrated on the global region, whether you are approaching the target globally or not. That kind of target is there. So that's why now we have seen, and with experience I am telling, CNN is the much better one for the accuracy point of view, for PSNR, all these things generation, SSIM values purpose. But GAN is means CNN is outperforming the generative adversarial net, especially for low resolution to high resolution, which is nothing but super resolution problem. So remaining cases, GANs are working very well when compared to CNNs.
Thank you, sir.
Yes,
We have one more query.
please.
how we can improve discriminator accuracy? Is it possible?
Discriminator is accuracy means by getting the output of generator, we are just getting the loss of discriminator and it will be updated. Discriminator accuracy is not at all important. Means once training is over, discriminator is not at all in the picture. Only generator will be there for the testing time. So discriminator should be quality should be improved. Then only generator quality will be improved, because if supervisor is not having enough knowledge, definitely student cannot gain the enough knowledge.
Gain much.
So this is all the same thing. So definitely we have to improve the quality of discriminator. So these are all like back propagation algorithms only should work.
Okay.
Any
Thank
other
you, sir.
queries? Any other queries?
Yes, sir. We have one more query.
Yes,
Do
please.
we have any advantage of auto encoder over GANs?
No, you can see this is only super resolution kind of issue only. Auto encoder is a kind of CNN only. So I would say that GANs are later versions or extended versions of autoencoders, which means GANs are having more advantage when compared to autoencoder. Whatever the advantages are there in autoencoder, definitely there with GAN.
Okay. Thank you, sir.
Okay, then
Any,
current, yes, please.
yeah, any other query from participants for this presentation? Okay.
Okay,
Thank you, sir.
right now 110. We will meet
Yeah.
again 120, 10 minutes or 5 minutes.
Sir, 5 minutes is
Okay,
fine.
okay, we can have 5 minutes only.
Yeah.
Okay, thank you.
Thank you, sir. Thank you, sir.
Hello.
Hello. Yes, sir.
Yeah, shall we start?
Yes, sir. Sure.
Okay. Uh, Now coming back to the applications case, like video surveillance applications, especially I will be discussing here semantic segmentation or motion segmentation, moving object segmentation in the videos. These are all three same only. Also, we call it as object detection in videos, moving object detection in videos. So here I will just giving the brief overview what is called moving object detection and especially the motivation objectives, what are the major challenges and how generally we have dealt with generalized pipelines for moving object segmentation and proposed contributions with experimental analysis I will be discussing here. Uh, so if anyone wants to work in this direction, I hope this will be the brief explanation and it will be useful for definitely for them. So if you are interested to work in this, please try to follow my content, whatever I am going to explain here. So introduction wise, like it is a pixel level classification or pixel level binary classification as like a foreground or background. For a given input video frame, I need to get the foreground region and background region. Means like foreground and remaining portion will be the background. So challenging, it is a very challenging task based on the usability like task and has extensive usability in the various real world applications. All surveillance applications require this moving object detection or segmentation. Then any kind of video processing applications or video processing algorithms definitely require this is the first step. As it is requires a first step requires as first step it is we need to work out on this one. So here practically the background or foreground may also show infrequent motions like in here. If you see in this particular one, snow is also actually under the background, but there is a motion in the snow. And similarly this water is also background, but it comes like a means there is a small motion in the water also, but it comes under background. Similarly water fountain, if it is there, so that comes under the background, but uh, it shows some motion, even somewhat larger motion only. Or waving tree, if we are collecting any video by keeping tree as a background, so that time those tree leaves can be wave, or that waving content can be considered as a actually should be considered as a background. But our algorithm is very means a very means we have to develop very robust algorithm like it should consider these things as a background. And more than 70% of data is relevant for further high level processing task. Reason is that if I go for video processing applications, and especially it requires for specific salient regions, maybe for object region. So that is the reason more than 70% of data is relevant. That's why background should be removed. These are all the kind of introduction as well as motivation case and high demand of various security based computer vision applications in surveillance or motion detection segmentation is one of the prime tasks for all these computer vision applications. And high level computer vision applications demands like this particular task only. And traditional methods generally we use like handcrafted algorithms, but these are not that much appropriate to give the results, and accuracy for of existing state of the art methods are still it is limited. And for real world applications or commercial applications, still it is this work is still under research, and it should come at the earliest. So this is only the target from the researchers. And also the reliability of these methods is restricted on unseen video data. So if I'm giving any unseen data, it is not very much appropriate results. It is not coming. And objective is like accuracy improvement for moving object segmentation algorithm in presence of weather degraded videos. Like as I said, it is surveillance applications. So in rainy season, rain may be there and rainy data will be there. Surveillance data, CCTV footage, and rain should be removed. And at the same time in traffic case and winter season there will be a lot of haze or fog, and even western countries snow will be there. So these are all the weather degraded situations, and that time also if you are able to perform the better segmentation, so then your computer vision applications performance will be improved definitely. So other thing is that camouflage kind of problems like background and foreground having similar kind of texture and similar kind of structure. So that time it will be very difficult to segregate. And if I'm talking about different types of challenges, these are all very major challenges for the moving object segmentation, like camera jitter. In some cases, camera may not be static. Like if I'm collecting the video with our mobile phone, so we generally hold with hand, and this hand generally it shakes. It even you are trying to keep it is very static, but it is not possible to keep. So that is the reason we need to go for the purchasing of tripod or all these things. But these are also kind of the camera jitter problem. So it may move frequently due to the physical influence or something else. If you are mounting your CCTV footage on a certain location, if wind speed is more, so that fluctuations will be there in the camera, and so that camera cannot be exactly same star, it cannot be static. So that time motion blur will be generated, or at the same time different images will be generated, which is totally different from the training. So this is one type of challenge. Another one is dynamic background. Dynamic background means like fountain regions actually comes under the category of background, but as this fountain content water is moving, so it will be considered as a background, foreground. So this is a very challenging problem, dynamic background. And another one is like sometimes like dynamic background means moving background also. If I'm collecting a video with moving camera, so that time it is background is also moving. It means it is very difficult to segregate what is background and what is foreground. Another one is illumination changes. Like with different lighting conditions, definitely data is changing. If training is done at certain illumination and testing is done at different illumination, it will be an issue. And another one is, as I said, is a camouflage problem. No, camouflage means like foreground and background are having similar kind of structure or texture. So that time it is very difficult to segregate what is foreground, what is background. If you see this is a aeroplane is there, it is very difficult to identify even with our eyes. Visually even it is difficult to identify, but here also this is somewhat difficult to identify what is foreground. Means if we see very concentration, then immediately we'll say. But the moment we see this image, it takes few seconds to understand what that object. It means it is totally occluded, it is kind of influenced by background. You will get a different understanding. So other one is challenging weather degraded situations like fog or smoke, or maybe in snow. Another one is shadows. So if it's like when person is when moving objects are moving, corresponding shadows will also move. But we can say like waving tree or the shadows also not actually the required target. Even shadow removal itself is a very big research topic. So people, there are several papers are there in shadow removal also. So this is also kind of challenging task. How to, because when person is moving, definitely shadow will move. But my target is that shadow cannot be considered as a foreground. It should be a background. Another one is night videos. In nighttime, visibility itself is degrading, and that should be improved first, and then only we can go for the uh, segmentation of foreground and background. So another one is intermittent mittent object motion. Let's say here this is an initially there is no object here, and car is moving on the bridge, and after that it is parked for some time, again started moving. So means initially there is no object, is a parking lot system case. Initial object is not present, and after some time means that time it, without car, that is a background. So when after some time car is parked, so then that time a car itself is background. Car comes under the background region only. So again, when car is moving, car becomes foreground. So we have to differentiate them in appropriate manner. Okay. And then coming to the generalized pipeline for moving object detection. Just a minute. Just 1 minute. I want to pick the phone call. Okay, sorry. Uh, Okay, this is the generalized pipeline, how generally it happens. Like this is an video frames, and on these video frames, I need to estimate the background first, and this estimated background from the estimated background and input frame, I will be getting salient region, means where actually likely the object belongs to the foreground, but these are also false content. So that's why again I need to go for one more network, means one more further processing for the appropriate content segmentation. So this is called this is actually generalized procedure for moving object segmentation. So here these are all the benchmark data sets which are available. If you want to work on this particular topic, you can go through these data sets. Change detection net data set. It is 2014. It was published, and it is having, this is the content. This many videos, 53 videos are there, and it is having various types of situations like bad weather, night videos, and so on. And these are all the number of frames, minimum number of frames to maximum number of frames present in the each video. And coming to another one is Davis. It got published in 2016, and these are all kind of statistics are available here. So another one is SecTrack data set. These are also statistics. So anyhow, this video is recorded, and even I can share this presentation. This is unnecessary waste of time to discuss about the data set, number of videos and frames, all these things. Clearly it is mentioned. So, and this is also another data set. It is especially for surveillance database for airport ground video. And this is underwater data sets. It is fish for knowledge data set. It is having 17 videos with various number of frames in each video. And now coming to the our contributions, like we have developed one algorithm that is for FGGAN. It is a cascaded unpaired learning for background estimation for ground segmentation. Here we have developed generative adversarial network. It was the first paper purpose for moving object segmentation using generative adversarial networks. So now, so here what we are doing here, we have trained our network in unpaired learning process. Here we doesn't require any specific ground truth for input. So ground truth, we are using different ground truth, means ground truths of different images as a ground truth, and input is different and ground truth is different. It will be trained appropriately. So there is a procedure for unpaired learning that you please go through that. It is a cycle again. Once you go through that, I think you can understand. But right now here I'm just explaining globally what exactly we are performing here. And here motion saliency is estimated with the help of estimated background and current video frame. And then separate unpaired network again we have developed for the once motion saliency estimated. We have gone for the foreground segmentation. And these data sets we have used the CDNet for the experimental purpose. See here we have used two networks. One is here I'm just explaining only generator network. First generator is performing for the background estimation, means it should remove the foreground objects here. Once it is done, you are getting the salient regions. And again one more network, one more GAN is used, and one more generator network is used to get the foreground estimation. So it will be utilized for, it is a supervised learning. Actually, you use the ground truth case unsupervised learning, unpaid learning we did. So here we have used the kind of architecture for residual as well as unit architecture for the this particular network training. And these are the training details. Initially, network is trained for background estimation, and then video frames and sample background frames are used for the training purpose, data is shuffled for unpaid training purpose. And foreground segmentation case, this is another network. Network is trained for foreground segmentation. Salience, map, and respect to ground truths are used, and data is shuffled for unpaid training process. As I said, it is unpaid. Data for ground truth purpose, we have shuffled them. And this is a background estimation. So these are all the some of the results for background estimation. This is the input image and corresponding background estimation using the traditional handcrafted algorithm. This is ours. So we can able to estimate the very appropriate background when compared to traditional state of sorry, handcrafted based algorithms. That is called histogram based background estimation. And then for these are all the foreground segmentation results. And these are all the visual results. Now these are for the existing results, these two. This is for proposed method results, and this is the ground truth results. We are able to achieve the state-of-the-art results that time, and even further we have improved these results using other contribution, other work. So here it is summary-wise, a novel cascade unpaid learning approach is proposed. And then learning based, it is here unpaid learning is applied for the background estimation as well as foreground segmentation also. Motion saliency once estimated, again it is applied for another network for foreground segmentation. Accuracy is examined on the CDNet dataset. And the scope for the improvement is like we need to check the temporal consistency. Actually, it is missing because each frame is considered as image and it is performed on that. But if we go with differently means if I can consider the few frames like current frame and previous frames outputs, so that it can go for the it can remove the temporal consistency problem. And another one is multiple ground truth background foreground requires. It means if you are having more data, it definitely can work. And parallel processing also possible if I can make the parallel processing with this video, because it is performing for current and previous 3-4 frames only. So that time if I can divide this network into means video into pieces, and if I can perform parallel processing, it can be done faster. And here to address some other part of the information and content as well as to improve the accuracy, we have developed this an end-to-end edge aggregation network for moving object segmentation. This got published in CVPR 2020. And here contributions to that, we have developed an end-to-end algorithm which uses multi-frame and multi-scale encoder decoder adversarial learning network is proposed here. And here we have also proposed a novel edge extraction mechanism. So here, as edges are very important for the foreground purpose or even for segregation of the background. So that's why we have utilized. And here also we use multi-frame pixel level, multi-scale encoder feature extraction. And we are that too, we have used the skip connections also, and dense residual blocks also proposed here. This is the actual network. So this is the actual generator network. This total is a generator network. We are taking the 3 current frame and 2 previous frames, and from there we are using one side is optical flow, and which gives the motion information. And similarly, this is our network edge aggregation network, and that it is edge embedding is performing here. Edge extraction module is this is the content. So it is like kind of difference operations is performing between the multi-scale responses, and from that we are able to get the appropriate output. And now coming to the training, we have done here a disjoint training and testing. Means people are doing like a training case. People what they are doing simply, let's say video having 1000 frames, first 100 frames are using for training purpose, and remaining frames are using for the testing purpose. But this is a this training is kind of scene data, or it is not disjoint. But here what we did, train with a few number of videos and test with different videos. There is no that whatever testing videos are there, we are not at all keeping them in the training. That's why we call it as disjoint training and testing. So, and cross data training means it is totally different to the training data set also. Data set to data set, it is changing. And the global training and testing means like now we are collecting the from each video, we are collecting few number of frames and training it globally and testing on the remaining data. Means for each video, it doesn't require any single, means require of single model. Means each video doesn't require the model. The means entire data set may be developed with single model only. We will be trained with single model only. And these are all the quantitative results and analysis. Our method is able to perform state-of-the-art performance when compared to existing methods. And these are all the visual results for Dijon training and testing data sets. Here we have done on the Davis 2016 data set. These are all global training on CDNet data set. Global training means we have collected a few video frames at starting of the video, and those video frames have considered for the single pool. Means so all together kept in the one pool, and then network is got trained. Remaining data is considered for the testing purpose. So this is a cross data. Totally we have trained on the natural data and tested on the thermal data. So with this we are able to, even though we are able to get the better results. And the overall summary of this application is like here in this contribution we have developed the dense residual blocks as well as edge extraction module. So these two are performing the improvement in the moving object segmentation task here. So with this I have completed. If you are having any questions, I think we can take up the questions.
Thank you, sir.
Any questions?
All the participants can mention their queries in the chat box. So we have one query.
Yes, please.
What is edge extraction mechanism?
Yeah, edge extraction means like you might have seen about Sobel operator. It is like edge extraction mechanism for the input image, but it is a simple traditional algorithm using the filter coefficients of like Sobel operator is like 1, 2 and 1, -1, 2, -2 and -1. So these are all the filter coefficients, but these fixed coefficients cannot, filter coefficients cannot perform the appropriate edges extraction. So that is the reason through network training only, these filter coefficients or filter parameters, hyperparameters will be trained or developed based on this particular training itself. So it can able to give the better accuracy. Our edges will be extracted very appropriately, which are actually required for the specific data or specific application.
Thank you, sir.
Yes, please.
Our next query is what is residual block and where it can be used?
Yeah, I thought CNN was discussed by earlier, means like other experts, but so these are all residual block is a well-known block. Means like to avoid the vanishing gradient problem, residual block has been proposed. Means if you are using two convolution layers and output of means like first input and one convolution layer and followed by another convolution layer. So two convolution layers are there. Output of second convolution layer. And if I'm using deeper network, like I'm using 100 convolutions or 50 convolutions, and it is slowly data is degrading. So because when convolution filter coefficients are between 0 to 1 only, and your input data 0 to 1. So when you are multiplying between 0 to 1 content, like 0.2 multiply with 0.2, you are getting 0.04. So means that value is always going closer to the 0. So if I don't correct or if I don't apply batch normalization, it is going downgraded. So that value tends to 0, and at last by the end of the last layer, so output becomes 0. That is a vanishing gradient problem. Gradient or output is itself is vanishing. So that is a major problem. So now to address these problems, we have proposed like generally we are using batch normalization, or this residual block has been proposed. Residual means like first convolution and second convolution is there, and again one skip connection means the same x is input, x1 is output of first convolution, x2 is the output of second convolution. X1 and x2 will be either concatenated or means added together. So that is a kind of skip connection. We call it as residual. Means wherever content is missing in these two, it will be again can be regenerated or can be adjusted from this. These two convolutions will work for the specific application or data highlightation, and whatever the data is missing, that will be regenerated or can be considered from the skip connection. So this is the major advantages. It is used for classification problem as well as regression problem. It is a very popular one.
Okay, thank you, sir. Our next query is what is how camera jitter is produced and how it can be eliminated?
Camera jitter is nothing but kind of motion. Means within the mobile means at camera itself some motion is occurred. So because of that some blur will be generated, because how motion blur will occur if you are collecting any camera photo, video or photo, immediately if you are moving, automatically motion blur will be generated in the image or video. So this is like because of if you are moving your camera within less time of the exposure time, that camera exposure time. So definitely motion blur is generated. To avoid that, you have to go for static fixing, and you need to know where to fix appropriately. Like there should not be wind problem, because of wind or air also. It can be having some pressure, and because of that it may create. So these are all like physical problems, like physical implementation or installation of this data or these cameras. This is the main problem, that there is no specific algorithm for that. This is only based on the, it should be solved from the way of fixing the cameras. Yeah,
Okay, thank you, sir.
yeah,
Our
thank you
next
so much.
question is if we are having jitter as well as noise. So,
Okay.
what among these two, which will be affecting our images more?
Jitter is means noise can be removed for some extent. But this motion blur removal is somewhat difficult when compared to noise, because noise, if noise percentage, even it is more, like if it is 70% of pixels are disturbed, even more than 50, more than 40, still it is a problem. But I am saying that if relatively, if motion blur is less and noise is more, that camera jitter is fine. But if noise percentage is less and motion blur is more, that other side, it is like it's very subjective matter. It depends upon the data. We cannot simply say in image processing simple justification or simple straightforward benchmarking is not possible. It everything is depends upon the data only.
Thank you, sir.
Yeah. Any other
Please,
queries?
please explain the process of salient estimation.
Salient estimation is very
Salient
simple one,
estimation, yeah.
because you are having already estimated background and input frame. So salient is nothing but it is very simple one, just subtraction between these two, or maybe you apply again two convolutions between these two and subtract. It's the salient content. Saliency region means where likely region belongs to uh, foreground, but sometimes there may be a false information, like background content also may be given as a sometimes as a foreground. So that is a kind of false positive that should be removed using further process. Actually here we are going for subtraction between foreground and estimated background, means sorry, input and estimated background.
Okay, thank you, sir. We have one comment from Dr. Gagan. Label
Yes.
can also be called as output.
No, label is a ground truth. Label cannot be considered as a output. Label is a target. So that we need to achieve by using our algorithm.
Any other query from the participants?
Someone has written difference between correlation and covariance.
Yeah,
Almost
so we have
same.
one more
Actually,
query.
almost same only. Correlation is like relating or similarity between two content. Covariance means actually it is also kind of similarity, even kind of cross similarity kind of thing. If we say means almost similar only. I don't say that both are different. Covariance and correlation are almost same. Even formula is also almost same. Even cross domain similarity sometimes we call as covariance. Even the through variance, like we will calculate the variance and from there we are obtaining, means more or less both are same from my side.
Okay. Sir, next question is how supervised and unsupervised are different if label cannot be called as output?
Supervised and unsupervised. Label should be target. Label should be target. And if I'm giving target, means don't say label is output. Target output. Output means generated by our algorithm. If you say target output, then it is fine. So when you provide target output for training purpose, that is a supervised learning process. Otherwise, it is unsupervised.
Okay, thank you, sir.
Okay.
We got the reply from Dr. Gagan.
Yes, yes,
His
I can
doubt
see
is
it.
clear now. His doubt
Yeah,
is
I
clear now.
can see it.
Yeah. Any other query?
So if
Okay.
not, I think
Thank you, sir.
we can close this session. And thank you so much
Yeah.
for this time.
Thank you so much, sir, for
Yeah.
such an informative session. We all are thankful to you for enlightening us by your knowledgeable words. Thank you so much, sir.
Okay. Thank you so much. So can I leave?
Yes, sir. Sure.
Yeah, and one more thing, if you are having any queries and questions, if you need some help, you can write to me. And if these are all appropriate and if we can solve them, definitely we will reply to you. Otherwise, even we can tell you, definitely we will get the reply, but please wait for some more. Sometime you may get reply even for sometimes 2 days or 3 days. Don't worry. Definitely you will get reply, but you write to me.
Okay,
Okay,
sir.
okay then. Thank you so much. Okay, bye.
Okay. Thank you, sir.
Okay.
Okay. Thank you, everyone. So we will start our next session at 2:30 p.m. So thank you. Email ID, Dr. Gagan is asking about email ID of the speaker. So we will try to arrange it and mention it on your WhatsApp group. Thank you.